Welcome to Analog Electronic Circuits. This is the 8th lecture, and today we are going to talk about the common gate circuit, and that is the agenda. So, first of all, a brief recap. We have so far studied two circuits. One is the common source amplifier, and the next thing that we studied was the common drain amplifier, right. Although it does not amplify voltage, it amplifies power. This is what we studied yesterday, and before that we had studied the common source amplifier. So, the common source amplifier gave me a gain, a maximum gain of GM RDS minus GM RDS, but if you do not say maximum, it is some RDS in parallel with some load. This is what we had seen earlier, and when you look at the common drain circuit, this gave me a voltage gain of GM by GM plus other things, GMB for example, GDS for example, GS, GL and all kinds of conductances. Notice in analog circuits you try to keep the dimensions, not just in analog circuits. Dimension analysis is a very straightforward way of checking the authenticity of the answer. So, look at the dimensions, right. First of all, you are talking about a voltage gain. If you talk about a voltage gain, then the overall dimensions will be dimensionless. So, I have got GM multiplied by some resistance, no dimensions. Here voltage gain, it is a conductance divided by conductance. Okay. So, keep track of the dimensions, it always helps. All right. So, this is what we had done in the last class, and today we are going to do the common gate. All right. We had discussed in the last class that in this course the bias is towards using the Norton equivalent method, and we are going to use the Norton equivalent method for most analyses. Okay. So, first of all, what is the circuit? The circuit has two parts. The first part is the DC operating point. Presumably, this is going to be my straightforward way of establishing DC operating point. Okay. And then what I want to do is, for the common gate circuit, I want the gate to be at what potential? Gate should be at, it is the common gate. So, the gate is common to both input as well as output ports, which means that gate is at the bottom, that is the gate is at ground. Now, obviously, over here gate is not at ground, in the circuit gate is certainly not at ground, but we can still implement ground in the small signal sense. How do we do that? With the help of a big fat capacitor. Right. Now, gate is at ground, and then what we are going to do is we are going to apply the input. So, source is going to be the input, drain is going to be the output terminal. Sorry, should have the big fat capacitor. We are going to couple in the input into the source, and we are going to watch the output at the drain. Okay, so, this is the plan. So, you have a question, the question is that why do not you couple in the input at the drain and watch the output at the source? Very valid question. unfortunately you will not get any gain whatsoever, because the drain is loose, right. You apply signal at the drain, nothing will happen on the back side, whereas if you apply signal at the source, something will happen at the drain. So, you can do that, that is, so the final answer is you can apply signal at the drain and watch the output at the source, but if you do so, you will not find any gain coming out of the amplifier. Okay. So, that is the answer. So, do not do it, basically do not make a circuit that is not very useful. So, this is the useful circuit where I apply input at the source and watch the output at the drain. All right. Now, what we are going to do is we are going to first make the small signal equivalent picture of this circuit, and to do that my first step is going to be to null the DC voltage sources, that is VDD, and the next step is going to be to make sure that all these big fat capacitors are short circuits in the small signal, in the incremental picture. So, for a signal that is changing with time, these capacitors are going to be short circuits. Done? So, let us redraw with these two changes in mind, and so after redrawing, this is what I obtain. At the source I still have RS, but RS and V in are together. It really does not matter what this is, it is just the voltage is just V in. So, the voltage at this node is just V in, that is it, there is nothing else over there. At the gate I have a ground, and R1 and R2 will not conduct any current because both of their terminals are at ground. So, at the gate I have a ground in the second picture, and as far as the drain is concerned, the drain has RD to ground and RL to ground. So, it is RD in parallel with RL to ground, and that is it, that is the entire circuit. So, this is the small signal picture of the common gate circuit. And notice something, we have not yet replaced the MOSFET with its small signal equivalent circuit. We are going to do that in our mind, we are going to try to do it inside our head step by step. Okay. So, avoid drawing the whole thing in the first step, right, let it remain as a transistor. Okay. I just want to point out that this is V out. Now, what we are going to do, how we are going to work this out is by finding out the Norton equivalent model of this entire box. Okay. So, let us try to find out the Norton equivalent of this entire box. Finding out the Norton equivalent involves two experiments. One experiment is to work out the short circuit current at the output terminal, and the second experiment is to look in from the output terminal and see what impedance is there, after of course nulling all the independent voltage and current sources. Okay, so let us do these two experiments one by one. The first experiment is to apply a short circuit at the output and to measure the current through that short circuit. So, let us redraw. Sorry, I wanted to make this wire in red. Yeah. This is I n, that is the Norton equivalent current. So, we have to measure that current. Okay. So, to start with, what is VGS? Gate is at 0 volts, source is at V in. So, VGS is minus V in. Is that correct? Is it understood? Gate is at 0, source is at V in. So, V gate to source is minus V in. All right. Now, recollect what is inside this MOSFET. There are 2 or maybe 3 elements, okay, 2 or 3 elements. One element is a GM. There is a GM, let us draw, because you are still not used to thinking about what is inside the MOSFET. I am used to thinking about it. So, this is what is inside the MOSFET. There is GM VGS between source and drain. Okay. There is also an RDS, and there is also one more GMB VBS. So, there are these 3 elements inside the MOSFET. Okay. Now, let us take care of them one by one. So, GM VGS, VGS is equal to minus V in, means that the current drawn by the MOSFET through this branch is minus GM V in. So, the current pushed outwards is going to be plus GM V in. So, I am going to try to write I n by inspection. So, this is the portion because of GM VGS. All right. Then the next portion, there is an RDS. So, I am trying to evaluate this total current. This total current has 3 components. One component is GM VGS, one more component, one by one. There is another component RDS, and RDS is going to carry the current because of voltage between drain and source. So, the source is at V in, right. So, what is the current going through RDS? In this direction it is in the opposite direction, right, but if you think, if you look going up the current is going to be V in by RDS. So, that is the direction of I n. Okay. And then the third one, VBS. B is also at ground and source is at V in. So, VBS is also minus V in. So, it is the same effect, you just get in addition GMB times V in. Okay. So, no circuit analysis as such, no KCA, no complicated KVLs or anything to be done. So, the Norton equivalent current is V in times GM plus GDS plus GMB. Is this okay? All right. Experiment 1 is done. Now, we go to experiment 2, and in experiment 2 what we have to do is, we again think like this. This is where my V in was, and V in has to be nulled for this experiment, which means you have to replace V in with a short circuit, which means that this resistor is as good as not there. Okay. And now, you have to look in from outside and tell me what is the resistance or impedance you see. Okay. So, source is at ground, gate is at ground. So, gate to source voltage is 0, body is also at ground. So, body to source voltage is also 0. So, inside this MOSFET there are 3 elements, right. There is GM times VGS, VGS is 0. So, that element is not doing anything, GM times 0 is 0. There is a second element GMB times VBS, and base is at 0, body is at 0, source is at 0. So, VBS is also 0, GMB times VBS is therefore also 0, which means those 2 elements GM and GMB are both not doing anything. Then there is a third element RDS between drain and source, and that is it, right. That is all there is to it. You are being asked what is the resistance, you look in from outside, it is just equal to RDS, that is it. There is just one resistor over there, RDS, that is the answer, done. So, my Norton equivalent model is built, right. So, the Norton equivalent model of this entire circuit looks like this. It looks like a current source, actually it is a controlled current source with a resistor in shunt with a resistor. This is V out, and then you can connect it to whatever else you want. Any questions so far? No questions? Great. This is good. Now, what is going to happen? You can solve this just by inspection. The current source is of value V in times GM plus GMB plus GDS, and at the output node you have got RDS in parallel with RD in parallel with RL. So, therefore, V out is going to be V in times GM plus GMB plus GDS times RDS in parallel with RD in parallel with RL, or if you like to write it as conductance, then you can write this as GDS plus GD plus GL. Okay. And therefore, the voltage gain is plus, this is a plus as in this positive not negative, GM plus GMB plus GDS by GDS plus GD plus GL. Is this okay so far? Actually, if you go back to the lecture notes from the common source lecture, right, there was also an RD over here. This RL includes RD. Okay. So, it was similar. All right. So, what do we have? Let us compile our list. Common source, the voltage gain was minus Gm by Gds plus Gl plus Gd. Common gate, the voltage gain is going to be plus Gm plus Gmb plus Gds divided by Gds plus Gl plus Gd. Okay. So, between the common gate and the common source, which is more? Look at the two carefully. One is minus Gm by Gds plus Gl plus Gd. The other is, denominator is the same, happens to be the same, just happens to be the same. Numerator, this one has just Gm, whereas here you have got Gm plus Gmb plus Gds, right. So, naturally the absolute gain of the common gate circuit is more than that of the common source amplifier. Fine. So far so good. Okay. Now, we have a few more things to understand. We have a few more concepts to cover, namely we have to cover the concepts of input and output impedance. So, output impedance we have partially, actually we have already done. When we are talking about the Norton equivalent model, we are already computing the output impedance. So, we have 3 circuits. The first circuit was the common source amplifier, and I am drawing only the small signal model over here. This was the common source amplifier. Then we had the common drain amplifier, and lastly we have the common gate amplifier. Okay. These were my 3 circuits. Now, what I want to know is what is the impedance looking into the circuit at the input, in these 3 cases. Okay. So, in the common source amplifier, the input impedance is infinite. Common drain amplifier, the input impedance is infinite, whereas the common gate amplifier, the input impedance is not infinite, we have to work it out. We need to work it out. Okay. The other two are obvious, because when you look into the gate, the impedance is infinite as far as we know so far. Is this okay? Then the output impedance, looking at the common source amplifier, for the output impedance calculation you are going to null the input, right, look in from the output. So, when I look in from the output, what do I see? I see R D on top, and looking into the drain of the MOSFET I see just R D S, right. So, Z out is nothing but R D in parallel with, okay, R L, let us say R L is outside, right, R L, the load is outside the circuit. So, it is R D in parallel with whatever you see down, looking down. So, it is R D in parallel with R D S. When we talked about the common drain amplifier, let us look in from outside, and what do I see? I see R S looking downwards, but looking upwards into the gate, into the source of the MOSFET, I see something, right. We did this computation yesterday when we studied the common drain amplifier, and we worked out the Norton equivalent model of the common gate amplifier. We will look at it once again. Okay. Then in the common gate amplifier, when I look in from the output, what do I see? Looking up I see R D, and looking down, remember this has been nullified, right. When this is nullified, the source is a short circuit. So, all I see is R D S. Okay. So, these two are obvious, these two are not so obvious, but are easy to work out. These two will work out, right. Notice that these two are also the same, right, just like these two are equal, these two are equal, these two will also happen to be equal, just check that, right. One is you are looking into the source, source has R S to ground, and then you have got MOSFET, gate is at ground. Okay. In this case you are looking into the source, source has R S to ground, gate is at ground, but then the drain has R D to ground. So, that is, there is a slight difference between the two, but nevertheless they are similar, right, slight difference. In this case R D happens to be 0, okay, just because we do not need it. All right. So, why are these input and output impedances important? Because these will give us an understanding of the power gain of the circuit. So, the input impedance, the output impedance, and the voltage gain, we have already worked out the voltage gain. Right, the voltage gain over here was how much? Minus G M by G D S plus G D plus G L. Here the voltage gain was G M by G M plus G M B plus G S plus G L plus G D S. Here there was a voltage gain which is more than that, G M by G M plus G M B plus G D S by the same denominator as common source. So, once again, why am I computing this? Because I want to work out the possible power gain, maybe I want to work out, or maybe I want to have an idea of whether the structure has any power gain or not. If I know the input impedance, I can work out what input source can drive the circuit, right. What can behave, what can work as an input voltage source, what kind of voltage source can drive this amplifier circuit. So, Z in is infinite over here. So, any source impedance will be fine, there is no problem. Here Z in is infinite, any source impedance will work out. Here I do not know as yet. Then here Z out is R D parallel R S, that can tell you what is going to be the voltage gain, right. So, any source impedance over here, that will give you the available power, input available power, and then Z out will tell you for maximum power transfer from this circuit what should be R L, maybe, right. Maybe if you place R L is equal to R D parallel R S, then you will get maximum power transfer into R L, right. Is that okay? But the gain also will change. Anyway, so you have to work it out, and so these parameters give you an idea of the drive strength, the drive capability of each of these individual amplifiers, and what is needed to drive these amplifiers. So, that is why they are important to us. Okay. Now, we are going to work out these two, this as well as this. I will actually solve this one and then plug in R D equal to 0 and obtain this particular impedance Z out. Okay. So, what I want to know is what is the input impedance of my common gate circuit. All right. Now, to do this problem, it is enough if you forget about R S. R S, so you look at the input impedance, you look down, you see R S, you look up, you see something else. So, the net input impedance is going to be R S in parallel with whatever you see looking up. So, it is enough if you forget about R S and just place R S in parallel at the end, right. Okay. So, let us forget about R S. Let us forget about R S and let us even further simplify and do this problem. How will you do such an analysis? You are going to apply a voltage source and see what is the current going into the circuit. Okay. Now, unfortunately, this is an impedance calculation, right. So, no other method is going to work out. So, we are going to apply a voltage over here, let us say V, and then we need to measure what is the current that goes inside. So, this is one of those very few situations where we are going to actually draw the small signal model of the MOSFET and then compute. So, remember this is G m times V G S where gate is at ground. source is V, this is GMB times VBS, body is at ground, source is at V, which means effectively this current is nothing but GM times V, this current is nothing but GMB plus V, GMB times V. Okay. This resistance is RDS. So, I have the following situation. I have a current GM times V going up. I do not yet know this voltage, let us call it something. Let us say this voltage is some Vx. Okay. I have another current GMB times V, and then I have a current over here which is V minus Vx times GDS. So, we can do a KCL at this point, V minus Vx times GDS plus GMV plus GMB times V is equal to Vx times GD. Is this okay? And then you put all the Vx's in the same side and the V's in the same side. So, V into GDS plus GM plus GMB is equal to Vx into GD plus GDS, and this gives you Vx is equal to V times GDS plus GM plus GMB by GD plus GDS, that is Vx. Now, this current is Vx times GD, and that happens to be the same as this current by KCL. So, the total current, let us call this total current I, right. This total current I is going to be Vx times GD, fine. So far so good. Then what is the input impedance? The input impedance is I applied V, I measure I, the input impedance is V divided by I, right. So, I have found out I, now I have to do V divided by I, and then the V of course will cancel out, correct, and therefore, the input impedance Z is going to be equal to GD plus GDS divided by GD into the other terms, GDS plus GM plus GMB, fine. Okay. Now, I will just rewrite this on the next page in a clearer fashion. So, this is the problem we have solved. So, looking into the source, the impedance happens to be GD plus GDS divided by GD times GDS plus GM plus GMB. Okay. And you can rewrite this, you basically multiply with RD numerator and denominator, and what you get is 1 plus GDS times RD divided by GDS plus GM plus GMB, right. And then if you want, you can further multiply it by RDS, both numerator and denominator. So, then it becomes RDS plus RT divided by 1 plus okay. So, this is how it is. Now, this expression happens to be something to memorize. This expression happens to be a formula, right. Remember the picture, you look into the source, drain is terminated with RD, what is the impedance that you see, and this impedance can be computed. There is a long drawn computation, right. This computation is not straightforward, right. You have to do some KCL and so on. It is not okay. It is a straightforward computation, but you will find that if you memorize this result, then a lot of things in future are going to be much easier, right. So, what you have to memorize is that the impedance looking into the source is RDS plus RD divided by 1 plus GM plus GMB times RDS. You could recollect, you could memorize this form or this form or this form, whichever suits you. My personal preference is this particular form. This is what I have memorized. Okay. This is an important result. Now, going back, so this answers this question mark. Over here you just plug in RD equal to 0, right. Over here RD is equal to 0, plug into the result and you get, if RD is equal to 0, you have got RDS by 1 plus GM plus GMB times RDS, and GM plus GMB, actually just GM times RDS is quite large, is not it? GM times RDS is quite large, that is the intrinsic gain of the MOSFET, right, which means this entire quantity is quite large compared to 1, and therefore, you can forget about the 1, RD is 0. So, RDS cancels out from numerator and denominator, just leaving 1 by GM plus GMB. So, this impedance is approximately 1 by GM plus GMB. This impedance has to be worked out, right. I mean it is this complicated expression, right. I do not have space to write it over there, but nevertheless that is what it is. All right. Now, this happens to be a formula that needs to be memorized. This is important. Okay. There are not too many formulae in the course, not too many, right. You can make do by memorizing just 2 formulae. This happens to be one of those 2. This is so important that this formula happens to be one of 2 formulae if you just want to memorize 2 results. So, this is one of those 2. what is the impedance looking into the source? The impedance is the sum of RDS and RD divided by 1 plus the intrinsic gain of the MOSFET. 1 plus the intrinsic gain of the MOSFET is GM plus GMB times RDS in this case, okay, because the source is moving around. So, therefore, GMB also comes into the picture. Fine, good. So, just like this result, this is one out of the two formulae to memorize. If you were to memorize only just two results, this is one out of those two. There is a second one, and we will just do the second one just to keep you on your toes. The second one is going to be this one. So, here instead of looking in from the source, the question is what happens when you look in from the drain, what is the impedance that you see, okay. And there could have been a third one, but that is trivial. Looking in from the gate, you always get infinite. So, do not worry about looking in from the gate, right. You either look in from the source, you see RDS plus RD divided by the 1 plus the intrinsic gain. Just by the way, is this large or small? If RD is equal to 0, this is a short circuit. Looking into the source, you see we just discussed 1 by GM plus GMB, okay, and that is a small resistance because GM is large, is a large conductance. Fine. So, looking into the source, you always see a small resistance compared to RDS. All right. Now, if RD had been there, if RD was infinitely large, suppose RD was infinite, then what would have happened? This is infinite. Infinite divided by something is still infinite. So, ZS is still infinite. Think about it. If RD is open circuit, then no current can enter this circuit, right. So, it checks out. So, both RD equal to 0, RD equal to infinity, it checks out. Then normally what happens is that this impedance is fairly low. So, looking into the source of the MOSFET, you normally see a low impedance. Normally RD is going to be off the range of RDS, right. So, RDS plus RD, these are two similar numbers. Normally you are going to see a fairly low impedance looking into the source of the MOSFET. So, the next exercise is what is going to be the impedance looking into the drain of the MOSFET. I suggest that you take this as a homework and try it by yourself. So, let us close this exercise over here. So, we have understood today more or less the common gate circuit. We have seen a few things. We have seen that the impedance looking into the common source circuit is very high. The output impedance is RD parallel RDS, gain we know. The common drain circuit, the impedance looking in is infinite, the output impedance is low because you are at the source. So, looking into the source, the impedance is low. So, the output impedance of the common drain circuit is low, and then the gain of course is less than 1. Then the third structure, the common gate amplifier, here the input impedance is low the output impedance is the same as that of the common source amplifier. The gain is a little more than that of the common source amplifier. It is similar, right. Here the dominating term is GM, right. So, GMB and GDS are much smaller than GM, which means that it is of the same order, right. It is slightly larger, just that it is positive. Okay, so, this is more or less what we have learnt so far, and in the next class we are going to continue from here. We have also introduced an important formula for you, right, looking into the source, what is the impedance, okay. And this is something, this question is something that you have to work out. We are going to work it out nevertheless in the next class, and that is going to be another formula. Okay, thank you.